going to take a look at 15-15, and this is a problem where we're trying to figure out what the velocity is at a point in time where we're given some information. Here's the force that the motor pulls on the cable. It's defined as F equals 10t squared plus 300 N newtons. So it's a function of T, and the crate is 100 kilograms. All right, so first thing is we recognize from this is that it's originally a rest. Okay, starting with the normal approach they follow typically with these problems is first, what are you trying to find? Okay, and this one's trying to find the velocity of the crate at t equal to 4 seconds. The second thing is what's given. And we're given a force, and force is a function of our force of the motor. There's a function of time and the mass of the crate. Okay, and the governing equation is just going to be the linear impulse and momentum equation. And this is for a system of particles. So this is the summation of the linear momentum for all of the particles and the velocities. So the masses and the velocities of all the particles. And here are the impulses acting on those. And here's the final mass is the mass, the summation of the masses of the particles times their velocities. Okay, so this is the equation. The next thing we can look at is the free body diagram with the, this is similar to what you'll see with the author's approach, then I broke it down into pieces. But free body diagram with the kinematic or the kinetic diagram. So you have these forces acting and a weight down, and then you have some velocity going up afterwards, right? So you have some causing some velocity in this direction, or at least we define this as positive as going up, okay? Well, we can follow the standard for this particular chapter. So what do we have? We have some initial momentum plus an impulse. So a diagram for the impulse results in some final momentum. Okay. And what thing you're going to recognize here is that there's zero velocity, right? Because it's a rest. So this is really just zero. Okay. So this part is zero. So we have some impulse and some final momentum that results from that impulse. Okay. And if we go back and just take a look at our governing equation for this problem, you know, this is zero, this term becomes zero, and we have some force acting over some time period and results in some, you know, mass, linear momentum at the end, right? This is the momentum. So one of the things is we know what T2 is. T2 is going to be 4 seconds. But the question becomes is, you know, what's T1? Well, if you look at, you know, our initial equation here, what we recognize is that some force is being applied. And if you say initially it'd be, you know, 300 newtons because T is 0. So initially it's 300 newtons. And if we take a look at the crate, you know, it's 100 kilograms times 9.81. So it's like 981 newtons. So what we see right now is that the summation of the force is actually down, right? At T equal to 0, there's a net force down. Well, the crate is just resting on a flat surface, so it's not like moving down. It's restricted from moving down. But what we need is essentially, you know, for T to get to a point where the crate starts to move, okay? And we can do that by just saying, you know, using the equation for a motion, Newton's equation for motion, F equals ma, and solve for T, okay? Where mass is going to be this, and the acceleration is acceleration of gravity, right? So what we could say is that it's mg, essentially, or the weight. So this equation essentially times T equals mg. This equation at T, you know, whatever T is, solve for T to find what that time is, T, for T1, okay? Okay, so just continuing on. So we need to find that T, or that initial time T, okay? So here's F equals the mass times gravity, right? So here's my F equals ma, right? So we don't have any motion, right? So until um, T is actually gets to the point where this force on the crate is more than the weight, okay? And if you solve for T, you come up with T equals 1.6432 seconds, okay? All right, and that's just going to looking at the free body diagram. Okay, so here's our linear impulsive momentum equation. And like I said, this is 0, of course, to start with. And then now this gives us a range of time is equal to mass times velocity, right? In this case, he just defined it as in the y direction. All right, so all you have to do is plug in for those times. You have T1, 1.6432, and then T2 is 4 seconds, okay? Perform the integration. And of course, there's two parts to this force, right? There's the force going up and the force due to gravity going down, okay? So that's this part right here, okay? So you have to, so what ends up happening is that the force of y is really just, it's multiple components. This is due to weight, right? And this is the impulse due to weight. And this is the the time range or the limits of the times, okay? So you go through and solve for v with your values of t substituted in after you perform the integration. And then when you do that, you come up with the velocity of this. So 4.05 meters per second, okay? That pretty much is the summary of this particular problem. So I think that probably the couple of things need to keep in mind, of course, is that you're not getting motion until until a certain amount of time has gone by, right? So we consider that part to be the impulse that's actually causing this thing to move, right? Okay. So that's pretty much it for this one. And the second one, you got to make sure that you have this component due to the weight, the impulse of the weight, essentially, right? Here's between the two times. This is the weight, and here's T1, and here's T2, okay? And that's it. And that's solving for that sort of that final velocity, basically our V2 velocity here, right, of the crate.